Thank you for joining us in this presentation introducing the W77Q Secure Flash Memory. Here at Winbond, we are very excited to introduce the W77Q. It is our third generation of secure flash memories, presenting a new approach for IoT security. In this presentation, we will talk about the W77Q as a hardware-based root of trust. This presentation is followed by additional presentations covering other key features and topics related to the W77Q. Trust is a major part of security. We consider our secure flash memories, the W75F and the W77Q, to be the foundation of platform security. In other words, the secure memory is the root of trust enabling system security. We designed the W77Q to be a hardware-based root of trust, as described by NIST. The W77Q implements hardware-based security functions, providing a set of trusted security-critical functions, which form the foundation for the secure operation of a system. NIST also describes the advantages of hardware-based root of trusts. Hardware root of trusts are preferred over software root of trusts due to their immutability, smaller attack surfaces, and more reliable behavior. And this is exactly what we did with the W77Q, being a hardware implementation of critical security functions, while leveraging the unique position of this root of trust within the same die of the flash storage device. In a world of exploding connectivity, security is a primary concern of any cloud service. The main goals for this security are securing each device and ensuring it runs authentic code as intended by the application designer, the ability to identify and authenticate endpoint devices, and the ability to provision new identities and services, which typically involves firmware updates. The W77Q supports these security goals by three of its security functions: the secure boot function, the secure firmware update function, and the remote attestation function. Let's see what makes the W77Q a cost-effective choice as root of trust for IoT devices and other connected systems. In their special publication, NIST states that the root of trust must provide a secure interface to access the security functions. Accessing the W77Q secure function is possible via a secure channel, allowing logically secure data transfer. Data is encrypted, authenticated, and replay protected using a unique single-use key. The W77Q took this a step further, and the secure channel could be established directly between a remote authorized user and the W77Q. The local MPU does not execute any security function, therefore the operation remains secure even if the MPU is compromised. Furthermore, the MPU does not have the keys or privileges to access the security functions of the W77Q, for example, to modify boot code. This reduces the surface of attack. The end-to-end secure channel is the cornerstone for most functions of the W77Q, as described in the rest of this presentation. The W77Q supports secure boot. This is a critical security function for any system, and its purpose is to assure boot code is authentic and in a state of integrity as intended by the OEM. Authenticity is verified when the firmware is updated and committed. The cryptographic write protection function assures firmware maintains its state of authenticity, and the integrity protection function assures firmware maintains its state of integrity. Together, these functions assure boot code is secure with respect to software and remote attacks. The secure boot is particularly suitable for ROM-less MPUs that boot directly from flash using execute in place. Placing the boot code in flash memory instead of ROM reduces the number of tapeouts and contributes to time to market. giving a clear advantage to our customers. After a device securely boots and connects to a network, it may require remote attestation. Device attestations involves establishing the hardware and software identities of a system. One system asks the other, "Who are you?" and the other system provides a proof of its hardware and software identities, which hardware is used, for example, a secret key, and which software or firmware is the system running. The W77Q supports this by giving access to its security functions. A remote authorized user establishes an end-to-end secure channel and then accesses the root of trust functions of the W77Q to measure the firmware, sign it, and report it back to the remote user. The remote authorized user could then establish the hardware and software identities of the device. Establishing the hardware and software identities of a system using the W77Q is a straightforward operation requiring two API calls, one to establish the end-to-end secure channel, and the second to authenticate the hardware and software identities of the system. Let's take a look how this process is simplified when using the W77Q. Let's say we have an IoT device with an MPU and the W77Q secure flash memory. And we have the remote authorized user, like a service running on a cloud server. The user is running an application and the IoT device is running boot code stored in the W77Q. All cryptographic operations are handled by the remote QLib, which is a software library on the server side, and by the hardware cryptographic engine implemented within the W77Q. Both of these components are provided by Winbond. And the final component is the secret key, shared between the user and the W77Q. The first step is for the remote user application to issue an API call to the remote QLib, instructing it to establish the secure channel. The remote QLib handles all cryptographic operation and sends a signed command to the W77Q to establish the secure channel. The local MPU only forwards the command to the W77Q via the SPI bus, but is not part of the cryptographic operation. Since the command is signed by the secret key, this process mutually authenticates the user and the W77Q. On the second step, the user application uses an API of the remote QLib to authenticate the boot code stored in the W77Q. The remote QLib issues the command to the W77Q. The W77Q uses its internal code measurement function to measure the firmware, sign the result, and report it back to the remote user. At the user side, the remote QLib goes back into action and authenticates the response. This authenticates the software identity of the IoT device as well as its hardware identity, as the signature of the response is based on a unique key known only to the specific W77Q. The remote QLib can then respond to the API call and return the authenticated software measurement to the application that can compare it against expected value, thus completing the process. The W77Q Secure Serial Flash Memory is introduced. It is a fully compatible drop-in replacement for standard serial NOR flash memories. The W77Q offloads security functions from the MPU into a single hardware solution, reducing the surface of attack, design effort, and required expertise. It is targeting remote and software threats, making it ideal for IoT security. And its features include platform firmware resiliency, secure over-the-air firmware update, root of trust, secure boot, and secure storage. Thank you for joining us. We hope to see you in the following presentations.